So today we're going to learn about bases. We already did a little bit with bases. You've learned a bit about Ks and Kbs, but we're going to learn a little more about bases and doing calculations with bases, weak bases. All right, so we have some generic reactions when we have a base. This reaction is a generic base reaction. A minus would be your base, and you always add your base to water, and you form the conjugate acid and hydroxide. So a base reaction, you're always forming hydroxide in the reaction. We also have what are called molecular bases, which would just be B for base. It's the molecular base because there's no charge on it. We still have to add water, so whether we have an acid or a base, we always have water and the acid or base as a reactant, sorry. And with a molecular base, we'll form Hb plus, because we have to have an H plus, which is the conjugate acid to the base. And again, we will form OH minus. So no matter what, with a base reaction, we form hydroxide, and the conjugate acid, right here, the conjugate acid to the base. The base could be an anion, or it could be a molecular base. And here I just have a table of Kb values in case we need them for our notes for any reason. We're not going to use them today, but it's good to have these in your notes. And notice hydride ion and amide ion have very large Kbs, which means those are strong bases. Okay? The rest of these would be considered weak bases because their Kbs are small. Very small compared to 1. By the way, they've given you units here. I got this off the internet, and we don't worry about units for Kbs ever, so don't worry about what those units are. And in case you're wondering, what's the difference between a molecular and an anion base? Right here, these three are your molecular bases. So ammonia, hydrazine, aniline, those are 3 examples of molecular bases because they don't have a charge. When you have a molecular base, the conjugate acid always has a positive charge. Okay? The first 4 examples are your anions, your bases that are anions. So anions can be bases. Cations, these over here, those are never bases. Okay. And this little line in note in red, this is very important. When a base is an anion, it's usually given in a problem as the sodium salt of the anion. We had that in the problems that we did in class the other day. Okay, so here's a problem that we are going to work on right now. Whenever you have a problem, first thing you want to do is figure out what is the reaction that you're working with. So we're told that we've got this chemical, and then note here, you're given a Ka for a different chemical. What you need to recognize is this piece right here. See how those look the same? So this over here, when we have sodium acetate, that's your acetate ion, I'm going to ignore the sodium, and acetate will be my negative ion. And notice that's the conjugate to acetic acid. Oops, H3O2. There we go. So I've got sodium acetate present in the solution. I don't have acetic acid present. I've given you the Ka for acetic acid, so hopefully you recognize we're going to need the Kb. You got to calculate a Kb for acetate. But we also need an acetate reaction. So a couple of things just to be thinking about. If you're given a Ka for an acid, but you've got a base in the problem, we need to find the Kb, and we're also going to need to write the reaction. And we don't write sodium in the reaction, we're just going to write the negative ion. We've got the negative ion. So this would be the form of the reaction that we're going to write. This A minus right here is the acetate anion. So here's my acetate anion. I add water to it. The reaction can go in both directions. I make the conjugate acid, and hydroxide. So a base should form hydroxide. Acids form hydronium ions. Okay, I can set up my icebox. 0.5. I don't have any of this stuff present initially, and I can ignore the water. The reaction has to go to the right because I don't have any product sitting around. So here's my first part of the problem. Oops. Okay, I needed a little more space. I had to hide that other part of the problem. Now I need a Ka, I need a Kb. We know that Kb will be products over reactants. I'm going to assume X is much less than 0.5. So this right here is approximately equal to 0.50 because X is so much smaller than 0.5. Okay, but I still need Kb. Well, I know Ka times Kb is 10 to the minus 14 for a conjugate acid-base pair. And I was given the Ka in the problem. Where is that? It's right here. There's my Ka. So now I can calculate my Kb. So my Kb will be 10 to the negative 14 over the Ka, 1.8 times 10 to the minus 4. And that is 5.6 times 10 to the minus 10. So I now know that this over here is 5.6 times 10 to the minus 10. So x squared is going to be 2.8 times 10 to the minus 10. I just multiplied both sides by 0.5. I take the square root of both sides and I get x is equal to 1.7 times 10 to the negative 5. Okay, so one of the things that students often don't do is they don't go back to the original question to find out what were they asking for in the question. What do we want? Oh, I want pH. So if we look at this big problem here, all I'm asking for is the pH right here. That's what I want. Try to find the pH. So I've gotten to the point where I know what X is, and X is my concentration of OH. It is 1.7 times 10 to the minus 5, which is the concentration of OH. So I can now get the POH, and from the POH, I can get the pH. There's a lot of steps in here. So POH will equal negative log of 1.7 times 10 to the minus 5, which is, it's 4.78. Now notice I added another sig fig. It's okay if you don't do this. When you take a log of a number, you actually gain a sig fig. Now that's the POH. The question asked for the pH. pH is 14 minus POH, which is 14 minus 4.78, which is 14, 10, 9.1, nope, 9.22. 9.22. Okay, 9.22. That's the final answer. All that work, given this tiny little bit of information, I have to do all that work to get to the pH. So you have to be very careful with these problems. Do you have an acid or a base, a Ka or a Kb? What's your reaction? What's going on? Okay, now, as part of your homework, you're going to do these numbers from Chapter 14. Make sure you do the numbers from Chapter 14, not from Chapter 13. Okay. All right. next thing we're going to do is acid-base properties of salts. I've actually alluded to this concept. We've learned that strong acids, their conjugate bases are neutral. They're even weaker than water. Water is neutral. So the conjugate of a strong acid is a neutral base. So it's not acidic at all. And the conjugate of a weak acid is a weak base. So here we go. In order to check if a salt is just an ionic compound. In order to check if a salt is acidic, basic, or neutral, we're going to use this information below, which is repeating things that we learned earlier. If you have an anion, we know that neutral anions, their conjugates are going to be strong acids, and basic anions, their conjugates, conjugate acid, will be weak acids. So if the conjugate acid of the anion is weak, the anion is a weak base. If the conjugate if the conjugate acid of the anion is strong, the anion is neutral. Okay. Cations. All cations are acidic, except alkali and alkaline earth metal cations. So we're going to do some problems here. We want to find out, are the following acidic, basic, or neutral? And then if we find that something is acidic or basic, we're going to write a reaction showing that. So we have to separate out the ions. We're looking at Na plus and we're looking at NO3 minus. So let's look at our rule. Cations. All cations are acidic except alkali and alkaline earth metals. By the way, cations are never basic, so if they're not acidic, they're neutral. Cations cannot be basic. Okay, so cations are acidic unless they're an alkali metal. Well, sodium is an alkali metal, so this cation is neutral. And silly me, I put a plus over there. It's not NO3 plus, it's NO3 minus. All right, so nitrate. Ooh, anions. What do we do when we have an anion? Let's read this carefully. Anions. We have to check the conjugate acid of the anion. So the conjugate acid, I add an H plus. So the conjugate acid would be HNO3. And the instructions tell me if the conjugate acid is weak, the anion is a weak base. Is this weak? HNO3. Hibber hickel high, hono hickel low, H2SO4. This is hono. This is nitric acid. It is strong. If the conjugate acid of the anion is strong, the anion is neutral. So the anion here is neutral. That's telling us that this anion right here is neutral. Therefore, the salt is neutral. We're done with that problem. Okay, next problem. If you want to do this on your own, go ahead and pause. I'm starting it up now. So I separate the chemical into the cation and the anion. All right, cations. They're always acidic unless they're alkali or alkaline earth metals. This right here is an alkali metal, so this is neutral. It's not acidic, and cations cannot be basic, so that cation is neutral. Okay, the anion, what do I have to do? I have to check the conjugate acid of the anion. The conjugate acid is HNO2. All right, what's my rule? What's my rule? The conjugate acid, I have to check if it's weak or strong. The conjugate acid is hidden. This acid is not strong, and if you're not strong, you are weak. So, if the conjugate acid is weak, where did we go? Weak, 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 weak. The conjugate acid is weak. The anion is a weak base. All right. So this anion right here is a weak base. Well, if I have something that's neutral with something that is a base, overall, this will be basic. If I stick this into water, the pH will be less than 7. Sorry, it will be greater than 7. Less than 7 is acidic. Okay, so we just learned that the salt is basic. And there were some more instructions here. If the salt is acidic or basic, we have to write a reaction showing that fact. Well, the reaction isn't going to involve the sodium because the sodium's neutral. So the reaction will involve the nitrite ion. Basic, we always add water to whatever the acid or the base is. If we've got a base, we better form hydroxide, right? Bases form hydroxides. So I also need a conjugate acid. So I get HNO2 and hydroxide, and there's my reaction. So here's my reaction showing that that salt is basic because it's producing hydroxide. All right, there are 2 more problems here. You can try them on your own. One thing about number 4, the aluminum, you've never seen these reactions for showing. You'll see it's acidic. And you will have to look at the notes to understand why that is acidic. Okay, but we're going to start with number 3. We've got Na plus, and we've got C2H3O2 minus. Okay, cations, this is an alkali metal. It is neutral. Neutral. Anions, let's get the conjugate acid, HC2H3O2. Is that a strong acid? No, it's not. So this is a weak acid. If the conjugate of the anion is a weak acid, then the anion is a weak base. Weak goes with weak. Strong goes with neutral. Okay. The conjugate is a weak acid, the anion is a weak base. I have neutral and a base, therefore this thing is basic. I put that into water, I get a pH greater than 7. Now I have to show the reaction. I don't worry about the sodium ion because the sodium ion is neutral. I take the anion, I add water to it, and if I said this was basic, I'd better form hydroxide and the conjugate acid, HC2H3O2 and hydroxide. There is my reaction. Okay. Last practice problem. Oh, no, there's 2 more. Okay, AlCl3. On that last one, I'm just going to put the answer up. I'm not going to go through it with you. All right, aluminum. Al3 plus, it's a cation. It's not an alkali metal. It is acidic. Okay, Cl minus. Oh, the computer is freaking out on me. Cl minus. The conjugate is HCl, which is a strong acid. If the conjugate is strong, then this is neutral. Weak goes with weak. Strong, the conjugate is neutral. Just like the strong base OH minus, its conjugate H2O is neutral. So any strong acid or strong base, the conjugate is neutral. Okay, well I have acidic and neutral, therefore this whole thing is acidic. I will never give you a problem where I have acidic and basic in the same problem. It'll either be neutral or acidic. Unless something is amphoteric. We'll talk about that later. Amphoteric is when you have a single ion or a single molecule that can act as both an acid and a base. And we've seen a couple of those over time, but we'll go over that. Okay, so I have to write a reaction. Al3 plus, how is that acidic? Well, here's the deal. We're going to learn about ligands a little bit later. And I don't expect you to be able to write these reactions yet, but this is an introduction to ligands. When you have a ligand, the number of ligands attached is twice the charge of the ion. And the ligand for these cations here are water. So, if the number of ligands are just things attached to something, to an ion, the number of ligands is twice the charge of the ion. So if the charge was 3, the number of ligands is 6. It's not that hard. And the charge, you just add up the charges of all the things, the ligands and the ion. Well, the ion was +3, water is neutral, 0. So the total charge here is +3. Okay, so that's my starting place. What happens here is I add water to this. I said this was acidic. If something is acidic, I better make H3O+, right? Okay, without me even telling you, you should be able to figure out what the other product is, but it looks really kind of strange. I need to take an H+ off of one of the H's here. So what I'm left with is Al. I'm only going to have 5 waters because one of the waters loses the H+, so that this water becomes H3O+. So I had 6 waters, and now I have only 5. One of the waters becomes an OH, and I lost an H+, so the charge also goes down by 1, and the charge becomes +2. And that is my reaction for that one. Okay, KCN, I'm just going to give you the final answer, so pause it right now if you want to do it on your own, and the answer is going to appear in a moment.